Yesterday's lesson, the segments that we were talking about weren't necessarily in the triangles, but I did say that we were leading up to talking about these segments within a triangle. So today we're talking about angle bisectors of the angles in a triangle, and we're talking about the perpendicular side, or the perpendicular bisector of the sides of a triangle. So what's important is that, of course, these lines are intersecting, but what's important to you is that they are not just intersecting, they are all concurrent. And what that means, as you can see on the screen, is concurrent lines are lines that are all intersecting in one point. And that happens so rarely that it is something of value to us. It is a property for us. And in a triangle, the perpendicular bisectors all intersect in a point, and we call that point the circumcenter. So let's take a look at a circumcenter of a triangle. Okay, so in this diagram, what I've created is the perpendicular bisectors of the sides of a triangle. Notice that they're all intersecting at this point A. Now, right now, this is just triangle Joe Schmo. Notice where the circumcenter is. Notice that it's inside of the triangle. I think it's always going to be inside of the triangle. Let's take a look. Notice where A is. Now it's outside of the triangle. Consider the triangle. What kind of triangle is this? What kind of triangle is this? Look at its angles. Say that again. It's an obtuse triangle. Okay, so it might be of note to you that in an obtuse triangle, notice where the circumcenter is. It's outside of the triangle. Earlier we noticed in this triangle that it was inside. What kind of triangle is this? It's an acute triangle. Well, how about if it's and it's not perfect, but what kind of triangle do you think that is? It's a right triangle. And it's not perfect, but the idea that I'm wanting you to get is that the circumcenter of a triangle will be inside the triangle when it's acute, outside of the triangle when it's obtuse, and on the triangle when the triangle is right. And we will actually be finding that circumcenter of a triangle, as you can see in problem 1. We'll be locating it, and it's not so hard, don't panic. Okay. So, and you'll notice on the bottom of the screen that the circumcenter is equidistant from the vertices of the triangle, and that's that big blank that you have there in your notes. That theorem about the circumcenter of a triangle, the big property about it is that it is equidistant from the vertices of a triangle. So what that allows us to do is I can construct the circle that touches all of the vertices of this triangle. Notice, no matter how I click and drag my triangle, oh, fiddle-dee, it messed up. I used the wrong center. Okay. That's my mistake. Let's try that again. I can construct the circle that will touch each of the vertices. Notice no matter how we click and drag this circle, this triangle, the circle is always touching its vertices. And the vocabulary term that we use, you'll notice in problem 1, they're not asking you for where is the circumcenter. They are asking you, as we can see on the screen, for the center of the circle that we can circumscribe around this triangle. So you might want to add that in your notes. Let's come back to that screen. Okay, so the circumcenter of a triangle is, we already said, equidistant from the vertices. Also, It is the center of the circle that can be circumscribed about the triangle. Okay, so just be ready for them to ask for that circumcenter in different ways. They might not necessarily just say, find the circumcenter. Yes?
What is circumscribed?
Circumscribed means that it's basically on the outside of the figure. It's touching all of the vertices of the figure.
So like the circle?
The circle, let's come back to that diagram. This green circle is circumscribed about this triangle because it passes through every vertex of the triangle. Have I answered your question? Okay. We've gotten from this screen what we need? If you already have and you're just waiting for us to move on, if you're looking at problem 1, you'll notice that I have a nice pretty grid there for you. I'm asking for the center of the circle that can be circumscribed about this triangle. So you might get started plotting those points, connecting the dots as neatly as you can. If you have your student ID or something else that's nice and straight that you can use to make straight lines, that might be helpful. Sorry, say that again? That it passes through all vertices. So far, all I'm wanting you to do is just connect the dots. I'm overhearing, I don't know what to do. Of course you don't. Not of course you don't. Certainly some of you have that intuition that you could take that next step even without my instruction. But don't panic if you don't know what you're doing. Alright, so the instructions are asking us, gentlemen, for the center of the circle that we can circumscribe around the triangle. In other words, we're being asked, find the circumcenter. In other words, what they're asking us for is find the intersection of the perpendicular bisectors. Now, realize what makes this particular example so lovely and easy. Notice that two of the sides of my triangle are a vertical and a horizontal line. And what's convenient about that is what's perpendicular to a horizontal line? A vertical line. And what's perpendicular to a vertical line? A horizontal line. Okay, so coming up with a perpendicular line isn't going to be difficult for us. Also, we'll think about that word, perpendicular bisector. So our lines are going to pass through the what of these segments? No, you're thinking further ahead. Think about that word bisector. If something is bisecting a segment, Eugene, midpoint. It's passing through the midpoint of the segment. So where would be the midpoint of segment BC? Well, you can just count the spaces. to figure that out. So how long is BC? It's 1, 2, 3, 4, 5, 6, 7, 8. So does it make sense it's 4 spaces in? 1, 2, 3, 4. So that's a horizontal segment. I'm going to draw the perpendicular line through it. It's here. Similarly, the perpendicular bisector of side AB, which is a nice vertical line, it's going to be a horizontal line passing through its midpoint, which is 2 spaces in, yes. And when I draw that perpendicular bisector, where do they intersect? Where do they intersect? 4, comma, 2. I heard something fantastically brilliant, I think.
I said it.
What'd you say? I don't even know what it was said, but I'm taking credit for it. Is that, no? You said it? No. Okay.
The midpoint?
The midpoint of what? Yes!
I just said the midpoint.
Absolutely fantastic observation. Yes. This is a right triangle. We observed in that previous screen, ladies, that the circumcenter was on the triangle in a right triangle, and more specifically, we just observed that it's on the midpoint, or it's at the midpoint. Maybe you want to write that down. That'll make your homework a whole lot easier. Okay, so this is the midpoint of the hypotenuse. So take a moment, please, and look at the your turn for that problem. Oh, I didn't give you a pretty graph. Do we feel like we absolutely just cannot function without a nice pretty graph?
Yes. How else are we supposed to do?
What did I just tell you?
Oh.
If you could kind of...
I don't know how to do it.
I'm sorry.
So far we have talked about the perpendicular bisector. Let's consider the angle bisector. Gentlemen and ladies, eyes up. Here is what I've constructed for you, the in-center of a triangle. The in-center is that point of concurrency of the angle bisectors. And once again, in this triangle, gentlemen, as I've drawn it for you right now, the in-center of the triangle is inside the triangle. Do you think that it will always be inside the triangle? Well, let's take a look. No matter what, it's inside the triangle. So what is interesting about, gentlemen, the in-center of the triangle? Well, remember that the incenter is the intersection of the angle bisectors, and in yesterday's lesson we realized that a point on the angle bisector will be equidistant to the sides. So what I pre-did here was measure the distance from that incenter to the side. And now notice what I can construct. Notice what is special about that circle in the triangle. It is touching each side of the triangle. Notice that no matter how I wiggle my triangle, it's always inscribed in the triangle. So the question was asked earlier, Mrs. Clouse, what do you mean by circumscribed? Remember, circumscribed basically means it's on the outside of the triangle. It's touching all of the vertices. Inscribed means basically it's inside the circle. It's touching all of the sides of the triangle. So in your notes, that blank is filled in by what is underlined on the screen. It is, equidistant from the sides of the triangle. Again, the incenter of the triangle is equidistant from the sides. And we have from this screen what we need. In problem 2, shh, gentlemen, in problem 2, this engineer wants to install a cell phone tower equidistant from the mall, the airport, and the subway. Today we've talked about 2 different kinds of points that are equidistant from 2 different kinds of things. So my question to you is, does this civil engineer want to figure out where the circumcenter is, or does he want to figure out where the incenter is? Incenter. Let's backtrack. Remember, the circumcenter is equidistant from points, whereas the incenter is equidistant from segments. Are the things he's trying to be equidistant from points or segments? Points. They're points. So what he wants is the circumcenter. On a problem like this, they're not asking you to figure out where that circumcenter would be. This civil engineer knows his way around a compass and a straight edge. He would figure that out. All they're asking you is which point would he be interested in, Adrian?
Wouldn't the circumcenter be outside of the point?
The circumcenter, you bring up a good question. Notice what kind of triangle this would be. It would be an acute triangle, and if you remember when we were wiggling that triangle around, in an acute triangle, that circumcenter is in fact inside. In problem 3, notice in the diagram what kind of markings there are. Notice that all of the angles of this triangle have been bisected, and that those angle bisectors are all intersecting at point G. And then from G, they've drawn GB, GF, GD, ladies, all perpendicular to the sides of the triangle. Once again, these equations set up exactly the way you think they would. Okay, so GB, you need to realize, is congruent to GD. And if you look at the question, they're not asking us for either one of those. They're asking us for GF, but conveniently, GF is congruent to both of them anyway. Okay, so you would set up your equation as 8x minus 7 equals 5x plus 8. Just like you did in yesterday's lesson. So 3x equals 15 when I subtract the 5x and add the 7. X is 5, and again, they're not asking us this time for the value of x. They are asking us for the length of GF, which I can find by plugging into either one of these. It makes no difference. So GB equals GF. Which would be 8 times 5 minus 7, or 33. Yes, ma'am?
How do you know that GB and GB are congruent?
Because G is the in-center of the triangle.
So it makes all of them congruent?
Yes. All right, please take a moment and work through the your turn for problem 3. Okay, we're looking like we're coming together with the answers to that. They are on the screen. If you haven't gotten it yet, just don't look.